Okay. A couple of quick announcements before we start this session. The first is that there's going to be this banquet tonight, and you can get drink tickets. You can get drink tickets for the banquet at the registration desk outside. So after this session, be sure to stop by, and you can pick those up. What? The banquet is here. It's going to be set up in this area, so we need to clear out after the panel discussion, which will follow this session. So there's an hour between the end of the panel discussion and the banquet, but everything is here. Good. So this next session will continue on the EHT theme. The first speaker is Monika Moskwa-Brodska, who's faculty at Radboud University, and she'll tell us about the EHT first results, physical origin of the asymmetric ring.
Yes, thank you. Okay, so as you can see from this animation, we didn't have to do any observations, really. We can make this kind of rings. Okay, so there are the 6 science papers, and so far you have heard more or less about first 4. And I've been involved mostly in paper 5, which talks about physical origin of the asymmetric ring. So this is the talk about it. So M87 is a low luminosity AGN, and this is like a standard picture that what we think is going on in terms of accretion and jet production in this kind of sources, and not only in M87, but also maybe in Sagittarius A star to some degree. So in the center you have a black hole, and then there's some kind of accretion disk, but this is not like a standard thin accretion disk like in bright AGNs. The accretion rate here is very small, so the inner portion of this kind of accretion disk are really puffed up. They are gas pressure dominated, they radiate very little, so this is sort of like an advection dominated accretion flow. And this kind of solution, started as early as in 77 by Ihimaru, and then, there was a very famous paper by Professor Narayan about this kind of models, and because this disk is very thick, it's probably also very easy for such accretion flow to support a collimated jet. And so far in M87, we haven't seen any of these, but we only see outflows. And basically the outflows, the semi-analytic models, you can produce the outflows and accretion separately, but not together. So we like to realize this kind of accretion scenario using general relativistic MHD simulations, because this kind of 2 inflows and outflows are together produced, together combined in one model. And together with magnetic fields. So this is more or less like this kind of models, numerical models of ADAF or RIAF looks like. And this RIAF is producing synchrotron radiation that we see. So there are a few universal features of this kind of accretion flows. You have some equatorial inflow, where basically you can have a different magnetization of this kind of disks. There's always some coronal outflow in a polar direction, and there is this highly magnetized funnel that very often is producing this kind of simulations. So the plasma density in this magnetized funnel is very low, and the physics that is operating here, it's happening here. It's more or less sort of like a pulsar magnetosphere physics. So you have some per-production sparks and so on. And in this kind of modeling in our project, we basically assume that this funnel is more or less empty, and we basically were not able to handle this kind of physics right now correctly. So we just pretend that we removed this region from the simulation. And there are global parameters of this kind of simulations models. There's a black hole spin, of course. This can range from -1 to 1. And this is one of the parameters that we would like to determine by comparing this kind of models to the observations. Another important parameter is the magnetic flux at the horizon. So here, this is given in some dimensionless units divided by some mass accretion rate. So this flux ranges in the simulations from 1 to about 15. And what does that mean in terms of physics? So this phi equal 1, we call this kind of simulation sane simulation, standard and normal evolution accretion flows, where you have very turbulent accretion disk and a weak jet. And on the other side of the spectrum of this kind of models, you have those MAD models, magnetically arrested disks, where basically the disk is very magnetized and the jet is very strong. And there are another list of parameters here. These are so-called post-processing parameters that you have to assume to produce, emission, to calculate synchrotron emission associated with this flow. So there is a black hole mass, mass accretion rate. This is just a scaling factor that tells you, how much density you have in this kind of model, because these simulations are dimensionless after all. And there's, of course, you have to choose a viewing angle to look at this model at the different angles. And there is this one question mark. The bottleneck really of this kind of models is the dissipation, where the dissipation is happening. So these accretion flows, both in M87 and Sagittarius A star, these are very low accretion rate systems. Accretion rates of the order, 10 to the minus 8, 10 to the minus 6, up to 10 to the minus 4 solar masses per year, so really low accretion rate, and the density is low, so practically this plasma is collisionless. So a species like, this is fully ionized plasma, so we expect that the species like protons or ions and electrons will thermally decouple, and this is a problem because, what we see is the synchrotron emission from electrons. So we have to make some kind of assumption on where the dissipation is happening, how to accelerate electrons, how to heat them up so that they will produce radiation. So from the simulation, we have this this number, the proton temperature. Protons are heavy, they dominate the dynamics and the plasma, the gas pressure in this kind of models. And we have to calculate this electron temperature to calculate radiation. And here we basically make an assumption, some kind of scaling law that tells us, how to heat up electrons in this kind of flow to calculate emission. And this function depends on beta, where beta is this is a beta plasma parameter, so the gas pressure to magnetic pressure ratio. And there are two parameters here, R high and R low. This, you can forget about it. This is 1. And then we change this parameter. And by changing this parameter from 1 to 100, we basically, heat up different region in this kind of accretion disk. So low R highs means that all electrons everywhere are very hot, and the entire region will produce radiation. But if we increase this number to 100, then we sort of like cool down the accretion disk, and only you have hot electrons along the jet, along the strongly magnetized jet. So this will sort of like light up the jet. So this is, like a basic model that we use. And, this is just an example how this kind of GRMHD simulation looks like at 230 gigahertz, which is, the observing frequency of the EHT. And here at this frequency, you're seeing, the inner edge of this kind of accretion flow. And for the different viewing angles, basically, we expect to see, either rings or a crescent or even a spot if you're looking edge-on the accretion flow. So the viewing angle for M87 is, we know it more or less from large-scale observation, from radio observations of a jet. It's about 20 degrees. So at least this parameter we can more or less fix. And we had this kind of models for years. For like last 15 years. But for some reason, most of the simulation basically has been focused on Sagittarius A star, not on M87. There are only a few models of M87. So these are just two examples of early models for M87 as early as 2012. But Jason Dexter, and this is a plot from my paper, that has been done, like prior to EHT observations. So here is the model. And this is the model that is convolved with the EHT array. So this is, if the source looks like this is what EHT would look like. So, with this is before the observation, so there's not much tuning here to any data, really. There was, and we could already make this kind of rings a while ago. So this is another motivation, You can use geometric models to, measure the size of this ring and put some physical interpretation on it, calculate the mass of this black hole. But if you want to explain the asymmetry of this ring or the variability of this ring, you have to incorporate some kind of more complicated models. So this is basically was our motivation to actually use this time-dependent GRMHD simulation to model the source, to at least learn something, where this asymmetry is coming from. So this is what the EHT collaboration done. So we have run as many simulations as we could within like 6 months. And then we have created this GRMHD image library that contain, this has been calculated using 4 different GRMHD codes and 3 different ray tracing codes, those post-processing radiative transfer codes. We have calculated various scenarios. We have in this library sane scenarios with weakly magnetized accretion disk and strongly magnetized magnetically arrested disks. We have calculated models for various spin parameters and also, accretion disk rotating, co-rotating with the black hole and counter-rotating with the black hole. We have in total more than 50 models. But these different models, we can also, paint them with a different electron heating and light up different parts of the models, and look at them at slightly different angle, 20 degrees and maybe 21 degrees or 22 degrees. So in total, we have, about 60,000 template images that we can compare now to the data. So here you see, a swarm of models, different images, and here is a zoom in to one of them, to 2 of them actually. So this is this match scenario, so you can see in detail how this image looks like. This is, I think, maybe time average image. So this is a total image, and here on this plot you can see basically origin of photons that are producing this kind of image. So, and here on these panels, you see we decompose this total image into image produced by photons that coming from the midplane of this kind of accretion disk and the near side and far side of the accretion disk, where a near side and far side is defined as, a region within 1 radian away from the spin axis of the black hole. And this green arrow shows you the direction towards the observer. So you can see that, in the match scenarios, for this kind of spin, most of the ring-like structure is basically emission produced by some kind of accretion flow in the midplane of the black hole. And this is another model. This is the weakly magnetized accretion disk. In this kind of models, we can produce more variety of these different images. This is sane simulations where you have most of the dissipation happening in the equatorial plane. Then you produce this kind of image. But we have also models where you basically can turn off completely accretion disk and only leave the emission along the jet. And then you will see the image in which the black hole shadow is illuminated basically by the far side, meaning the emission produced by the jet that is behind the black hole, the counterjet. And in this kind of scenario, you can also see some extra emission, in front of the black hole. So it's a little bit obscured in front of it. So we have many of these models, and we made this fitting, and we hope that we can learn something about, the weather around the black hole. And so here you have these models. This one of the models here, and again simulated EHT observation. And here is how this model looks like compared to the data. So it's been said in the previous session that we have like different data products, some visibility amplitude or even disclosure phase. And here the model is shown as a green point, and the blue points are the data. And this movie is variable. The movie duration is 5 years. So, this source wouldn't change so quickly. So my colleague Avery, in the next, one talk away from now, will tell you about the details, how we actually compare the models to the data, and how do we choose which model is actually consistent with the data. So I will leave it to him to explain this to you. And here I just wanted to say that one thing that we have learned from this model comparisons is something that we wanted to learn actually, what is the origin of the asymmetry of the ring. So we figured out that to make this kind of image that is brighter on the southern side, you have to orient the black hole spin in a certain direction in the space. So the spin has to be, pointing away from us. From that, we know that, we get also some kind of sense of rotation in this source, that it has to be clockwise on the sky. So this is it in terms of EHT data. We have also, it's important to say that we have also other constraints, observational constraints that constrain our models, and these are like 3 additional things. Like a constraints criteria that our models has to satisfy to be consistent with all these other observations. So I will just go quickly through all of them. So the first constraint is radiative equilibrium. We can calculate the so-called radiative efficiency of our models. This is the definition. And here the bolometric luminosity includes, of course, synchrotron emission, but also other radiative processes that are happening in the models and in the source, which is the synchrotron, self-synchrotron Compton, and the Bremsstrahlung emission. And we basically have to reject all the models that have efficiency larger than this classical thin disk model efficiency, which is like something like 0.4 at maximum. It also depends on the spin. And we find this model that this kind of models would be just self-inconsistent. They would just are expected to cool quickly. And this criterion basically, based on that, we can reject some of the math simulations with hot mid-plane electrons. All the same simulations are more or less fine. Another important constraint comes from the X-ray observations. So EHT has been observing together with Chandra. I mean, not together really. Chandra was observing like a day later, and there are also new star observations, and we know that around the same time what was the X-ray luminosity of the source, and we can basically use this as sort of like an upper limit. Our models cannot be brighter than that. And we basically compared our synthetic SEDs produced by the models to this luminosity, and we basically reject those that overproduce X-rays. So X-ray luminosity is very sensitive, what you assume about the particle dissipation. This is something we expected. And low values of R high are disfavored. Overluminous models are all the same models with hot electrons in the disks with negative spin. I will show you a table at the end that summarizes all of this. But there's a third constraint is the jet power. This jet power constraint comes from many different observations, from radio X-rays, from how much energy is deposited in the radio lobes in M87. This estimates range from about 10 to the 42 to 10 to 45 ergs per second. So we can, adapt, again, some conservative lower limit on the jet power that has to be produced in our simulation to satisfy this criterion. This number is 10 to the 42 ergs per second. And, we define this jet power in our models, as a total energy flux in the polar region where beta times gamma is larger than 1. We can also, there's also this P out. This is total power, total energy flux in not just in a jet, strongly magnetized jet, but in all outflows produced in the simulations, including, wide angle, low velocity winds. So this is sort of like a maximum, power that we can produce in the models. And this constraint is actually pretty strong. It's very hard to produce this kind of powerful jets. So basically, based on this, we can reject all the models with the 0 spin. They all have, jet power equal 0. And they have also, total power in all winds produced in the models much less than 10 to the 42 ergs per second. Jet power also, this favors all the same models with the spin at absolute value of a spin less than 0.5. But most of the magnetically arrested disks with highly spinning black holes are acceptable. And in our models also, this P-jet, jet power is always dominated by the pointing flux. So that tells you something, whether this Blandford-Znayak process is operating in the source or not. So here is a sort of like a constraint summary. So here you have a list of the different models, sane simulations and mud simulations. Second column is the spin of the black hole, and this R high is a parameter that tells you something about, how do you heat up electrons in the models. IAS is basically our sort of like a criterion that Avery will tell you more about later whether the model is consistent with the EHC data or not. So pass means consistent, fail means inconsistent. So as you can see, many of these models passes this, so it's consistent with EHC data. This is the radiative efficiency of the model and X-ray luminosity of the model. As you can see, many of those models fail to reproduce this minimum jet power, this 10 to the 42 ergs per second. So yes, almost done. So this is a summary. So standard GRMHD, the ring shape and asymmetry, this is all consistent with GRMHD simulations. And also including earlier models and of these observations has been done. So the inferred black hole mass by fitting the models to this kind of models to the observations is also high. And Dom and Avery will tell you a little bit more about it. But this black hole mass is consistent with the stellar dynamics, but not with the gas dynamics estimates for the source. But this is actually, I put a smiley here because this is actually funny, because what you're seeing in this plot is actually a gas, probably a gas. So a gas is ruling itself out. Okay, so there are other alternative explanations to produce this kind of rings that we were thinking about. This could be also a jet feature, this kind of circular rings. However, are typically not seen in a large-scale jet. We were also thinking about, maybe it's an Einstein ring or some counter-jet feature, some hotspot in a counter-jet behind a black hole being lensed. But that would require very, fine-tuned alignment. And there's always a question about how stable this kind of feature would be. And we know from previous observations, that has been reported in 2012 and 2015 that, the source size measurements with the smaller array was more or less the same as this 42 microarcseconds. And there are a bunch of other, alternative to standard GR models, GRMHD models. They are very difficult to rule out. And many of them also predict shadow features, different type of objects that, are easily can mimic a Kerr black hole. Here I just listed some of them. There are boson stars or wormholes or some Grava stars, things like this. But we don't have all these models at hand to make comparisons. But the most important thing that hasn't been mentioned yet, I think today, is that together with this picture, we also released the data. The EHC data is publicly available. Anybody can go to the EHC webpage and download it. So if anybody has some alternative to standard GR model, it's there to, anybody can make a further comparisons. And just one more slide. This future is, of course, we also want to look at the polarization of the ring. We have this data, and this is just a simulation, of course. We have also, some models or ideas how this source should look like in the polarized light. And, the idea is to put, more stronger constraints on the magnetic field geometry in the source. Okay, thank you very much.
Okay, maybe, Dom, please.
This is kind of a naive question. So why isn't the fact that we're looking at this from an angle more obvious? And in particular, naively, I might have guessed that the brightening just comes from the fact that we're kind of looking at say that that's not true. How that's coming from.
From rotation.
Yeah.
It's this kind of bright features you can, so.
Is it true that the bottom half of the figure, is that the one that's closer to us?
No, it's just coming at you. This gas is coming at you. We think that this is a Doppler boosted emission that, it's brighter because it's Doppler boosted because it's moving towards you with almost speed of light. Because, you have some rotation in the source. Either the black hole is spinning or matter is spinning around, rotating around it, or both are rotating. And this lower part of the picture is just basically moving towards you. That's why, it appears brighter.
Which direction is the jet pointing?
So Jeff said it's pointing this way. It's going this way.
Yeah, sorry.
Yes.
It's surprising that it's not obvious from the picture to me. Maybe I'm just being naive. Looking at it, there's an angle. We're not looking at it
well, 20 degrees is almost at the face on, right? It's almost. Yeah, but if the angle, if the angle would be different, I mean, 90 degrees, then you would just see, crescent brighter on one side. If you look exactly face on, everything would be symmetric.
Okay,
That's
so
what the models tell us.
I think we should move on. Maybe Dom, as you get set up, we can take one more. I think Eric had a question.
I'm curious about the discrepancy in the mass estimates. Is it known why the stellar and the gas dynamics estimates differed so much? Is it that one is more sensitive to dark matter than the other, the stellar estimate?
Well, I would say that, gas is always, sensitive to all, not just gravity, but other forces, like even pressure gradient forces. So, it doesn't have to be, virialized or anything. So, yeah.
Let's thank Monica again. Okay, next up we have Dom Pesce. Dom is a postdoc at the Black Hole Initiative, and he'll tell us about geometric modeling of the emission structure.
All right, thanks, Michael, and thanks, Monica. Monica just told us all about these simulation library and all the really hard work that went into getting the detailed physics and the detailed structure of the emission, or what the emission might look like in around the M87 black hole. But going back to the image for a moment. We want to try to model this. We want to try and take these simulations, or take something we would like to know and extract that information from the data in some way. And fitting these simulations seems really hard. And we did it, but I'll save that for Avery. Just looking at the image, it's really it has a pretty simple apparent structure, right? And so it's sort of just a ring with some asymmetry to it, and it's pretty natural to go ahead and try and just model this thing in a very geometric manner. Just try and extract the sort of characteristic features, a small set of parameters that can describe the geometry of the emission structure that we're seeing in this system. And one of the primary advantages we would get from this sort of approach is that simple shapes like circles and disks and things have analytic Fourier transforms. So if we want to fit directly to interferometric data, we can produce visibilities analytically if we're using a simple enough model. And we can construct such a model in a pretty straightforward way. So we start with something like a circular disk. This has a Bessel function Fourier transform. We can remove another disk from the inside of it, so a difference of two Bessel functions. And then we could scoot that over, which is just going to be a phase shift of the interior subtracted disk. Rotate the thing around. Rotations in the image plane and rotations in the Fourier domain are the same. And then blur the thing, right? So we're getting something that looks an awful lot like the image already. Blurring by a Gaussian is a convolution process in the image domain. That's a multiplication in the Fourier domain. So this is all mathematically well understood, pretty straightforward procedure. And we've obtained something that looks a lot like the image already. I mean, this is schematic, but we can go ahead and try and fit a model an awful lot like this one to the data and see how well it does. So being just a bit more systematic about how we actually go about putting these parameters together, here are diagrams directly from paper 6 that show two geometric models that we did, these sorts of crescent models that we did fit to the data. And then the parameters there on the left that we actually used. And these were mainly constructed to have, to really target certain properties of the emission structure that we thought we'd be interested in. Things like the size and the width of the ring, right? The asymmetry of this structure, the depth of the shadow interior to the ring, the sharpness of these edges actually is something we thought we would like to have a handle on, and of course the orientation itself. We gave these things names in the papers, just to distinguish between them. These were the excess ring and the excess ring Gauss names. They aren't such great names, so we put out a poll to the whole collaboration and asked what they would like to call them. We didn't get that many responses, but the best responses we got were the other ones here, so the Ringo and Ringo Starr. Yeah, courtesy of Maciek Vilgas. When we tried to fit these things, there were some of these parameters that ended up being a bit. It turned out that the data constrained them a lot better than the others, as it's wont to do. And so I just colored here using a two-color scheme the diameter, the depth of the interior shadow, and the orientation of this crescent feature turned out to be things that we were able to measure pretty well or put pretty tight constraints on. And these other three, the width, the asymmetry, and the sharpness, we either have upper limits or only a poor handle on from the data at the moment. But I'll walk through this now. So the way we went about this fitting procedure is using a pretty standard Bayesian inference style formalism. This slide's just for the sake of formality, tossing up our likelihood functions. We used two different codes, two different algorithms to fit these data. That was the two different models, one for each of these approaches we took. So the one on the left here is a method where we fit to the visibility amplitude data quantities and the closure phase data quantities that you heard Andrew talk about in the earlier session. And you might remember that the visibility amplitudes have these gain factors, these station-based gains that modify the intensity and can change with time. So those are these little G factors in here. Those needed to be modeled along with the geometric emission model itself in order to fit to visibility amplitudes. The other approach used purely what we call closure quantities. So in addition to the closure phase that Andrew mentioned, there's an analogous quantity for the amplitudes called closure amplitude. And these things are both gain and variant. They don't depend on any station-based gains. Those all cancel out. So we did these two fitting procedures using two different, effectively representations of the data. Again, this is more of the trying to be as redundant as possible, so that we're not subject to the vagaries of any one approach or any one way of representing the data. And being one of these inference-style problems, we used sampling code. So this is a schematic illustration of how a nested sampling code runs, but we also used an MC code as well. And this is just showing that as you vary these parameters in a way that's guided by the shape of your likelihood function and the priors you've imposed on the parameters, you can flesh out the posterior distribution and get constraints on the parameters of interest in this way. And this looks a lot like the one we ended up with just fiddling around with the data. And so with some particular ways of handling some of the systematics in the data sort of being swept under the rug a little bit here, the fit quality was really quite good for these geometric models. So this is showing the fit to the visibility amplitudes, the closure phases, and the closure amplitudes here. And red and blue are going to be thematically just these two different codes throughout this talk. And the residuals we get are pretty consistent, chi-squareds of order unity across the board, and with no real systematic residual structure in any of these plots down here. So fit quality seems pretty decent just with these geometric models. And looking at the posteriors themselves for the actual fit. So again, we had these two techniques. I've put up the references there. But the posteriors that we're seeing for both of them are pretty broadly consistent for all the primary parameters that we were interested in. There are some systematic differences, particularly in the width that we think we understand, having to do with different definitions of the two models and the ways in which the two different data products interact with particular transformations that we've chosen to perform. But by and large, the posteriors are really, really quite consistent, and the values and uncertainties that we get on each of these geometric parameters match quite well between both approaches, and also across all four observing days and both observing bands. So we fit each of these data sets independently. So the primary parameter of interest, right, the number one thing that we're most concerned with is the diameter of this ring. And so here is a plot showing for both of these codes and then a combined fit to high and low band on each day, what the recovered diameter measurement was along with its uncertainty. And we get really tight constraints, really consistent constraints across the board on the diameter. It's really a little bit more than 40 microarc seconds across with a quite small statistical uncertainty there of only a couple percent. The other parameters are generally somewhat less well constrained, and there are hints that some of them may be evolving between the first two and the last 2 days, as is sort of consistent with what Maciek and Andrew were discussing. That we know there's some evolution here, but the global constraints that we get, or this ring, the width of the ring is finite, right? It's not a filled-in disk, but we only really have an upper limit on it. The fractional width, the width over the radius, is something about probably less than half or so. But the width turns out to be a quite difficult parameter to constrain with the current data. The ring edge, we tried to determine how sharp this thing was, and that actually ended up being reasonably well constrained. It was not super sharp, but again, a fractional sharpness, so the sort of Gaussian width of the edge over the radius, about 20% or so, or less than that. And then the central region is really quite dark, and this is one of the better constrained parameters, and is consistent with a lot of the work that was done in the imaging, which is that the region interior really seems to be suppressed relative to the emission in the ring by a factor of 10 or more. 10 is actually quite a conservative number that we use here. Is really the top of the error bars up here shows we're just peaking up above 10 to the minus 1. Most of the constraints are substantially less than that. So it really is a substantial flux depression in the middle there. And so the reason we really care a lot about the diameter, and the reason that's the most important parameter for us to recover, is because we can use the diameter to estimate or measure the mass of the black hole. And the reason we can do that is because within the context of general relativity, in this case specifically for a Schwarzschild case, there's this well-known result that the mass of the black hole scales the size of the observed lensed photon ring, what we're calling the size of the black hole shadow, what we think is contributing here to the shape of the emission region. And so within Schwarzschild, that prefactor that scales the Schwarzschild radius is square root of 27. We actually measure an angular size on the sky, so we've got to divide by the distance. And we like to think of this thing in terms of sort of a natural angle, what we call the gravitational radius in angular units. So the angular gravitational radius. So what you might expect for Schwarzschild in GR is that if you were only looking at the photon ring, you'd see something like 2 times the square root of 27 times the angular size of the gravitational radius would be the size of the emission region that we see. That would be about a factor of 10, 10.2 or so, some small dependence on the spin. But in practice, we know that we're not just seeing emission from the photon ring. There's other material around there that you saw in simulations that Monica showed. There's a particular choice of geometry that we've chosen with this crescent model. It's not necessarily tracing exactly the photon ring. So the scaling factor is sort of actually unknown a priori, and we calibrated it using that GRMHD image library that Monica told you about. And here's just a plot illustrating how we did that. We divided it up into a couple of parts. We used many, over 100 of these images from the library to make this calibration, fitting crescent models to each of these images and trying to back out the size of the emission region in terms of the gravitational radius. And the scaling factor we ended up deriving was about 11.5 rather than something like 10.2. So it's like a 10% larger effect, and that's combining something about this fluffy emission with something about the particular model choice we have. And when we throw all this into the mix and we measure the size of the gravitational radius for the system, we get about 3.7 and change microarc seconds is the angular size of the gravitational radius, which remember is about 1 over 11.5 times the actual size of the thing, with, again, very small statistical uncertainty just associated with our ability to measure that diameter, and a substantially larger systematic uncertainty associated with the calibration procedure itself. There's a pretty big slop in how one can translate between the size of the emission region and the size of the gravitational radius. When we use the distance measurement to the galaxy, we can convert this angular size to an absolute size and therefore to a mass of the black hole. And from the geometric modeling alone, we get about 6.5 billion solar masses. That's just one of 3 techniques that we used. The other 2 are coming up in the next 2 talks. So I'll just leave this summary slide up here and take any questions. Thank you.
Great. Questions? Maciek.
You just gave some error bars there. so?
Yeah, so the distance uncertainty down here is included in this final mass measurement, but it has no bearing on the size, the angular size of the ring, or the calibration from that diameter down to the gravitational radius.
So the number in bold is with
The number in
distance
bold includes the uncertainty associated with the distance, yes.
Right, thanks.
Ramesh.
So Dom, you had some measurements of the width of the ring,
Right.
right? And you had an error bar. And none of the error bars reached 0. Can you actually rule out a very thin ring based on your model fits? Because that would be a very interesting result.
Right. No, I would say that we aren't measuring. So you're talking about this plot.
Yeah.
Yeah. So none of them go all the way down to 0, but they're all consistent with 0. So the width is a parameter that we chose to be positive definite, right? We imposed a priority. These things can't go below 0. They can only sit near 0, and all of these measurements are consistent. Like you can that posterior is very consistent with going pretty much all the way down to 0. I don't think we would be able to distinguish between what we've measured right now and delta
On
ring.
all 4 days.
On all 4 days.
Okay.
Any questions for Dom? One check.
Right.
And your code had, I noticed those correlations between the closing quantities.
Yeah.
And that's how it was running.
Right. So the likelihoods you're seeing up here are actually the likelihoods that were used in the model.
Did you actually compare your code with and without those correlations?
You're saying, did I use this code without including the correlations?
And compare the same code but with and without off-diagonal terms in correlation mapping?
I've done that on test data problems. I have not done it on these data. I didn't bother running it without the correlations. No. Of course I could. I didn't. But no, I mean, this is the correct likelihood, so I didn't run the incorrect one. Yeah. The way at which it matters is model dependent, and it's a reasonable question actually because I don't know how it's going to affect this model. Yeah. No, it does. Toy models, you can see the difference in the posterior as a result of including the covariance. Yeah.
Okay. Avi?
So I was just wondering how much uncertainty there is in the systematic possibility that perhaps the accretion disk is not ending near the ISCO the way we imagine it. So can you elaborate on that and how sensitive is the error bar in the mass estimate in terms of the truncation, the way the brightness drops? I mean, simulations are reliable in terms of the gas flow perhaps, but still we don't fully understand the emission.
Right, so this systematic error bar here is entirely derived from the GRMHD image library, right? So if there is behavior that's not captured by those simulations, then this systematic error bar will not account for that behavior. So this is really only saying what are the range of gravitational radii we would ever get from fitting these sorts of this sort of model to underlying structure that looks like something that's come from the GRMHD simulations.
So if Changpei Ma measures the mass to be 3 times 10
Yeah.
to the 9, then what do you need the models to do? Emit closer?
Yeah, so I mean, if the real mass were something like 3 versus 6 billion solar masses, then that means that this calibration factor is not right? That means that something inherent in how we've done this calibration was systematically wrong. Yeah, I like to think that's not likely.
But that's the theorist approach.
Sure.
Okay, we should move on, so let's thank Dom again. Okay, so our next speaker is Avery Broderick. Avery is faculty at Perimeter Institute and University of Waterloo. And today he'll be telling us about confronting GRMHD simulations with data.
All right, good, it came up. Hello, I'd like to thank the organizers. It's been very interesting, very exciting conference as always, and I'm always happy to be back in Cambridge. So as Monica alluded at the beginning, I'm going to be talking about trying to compare GRMHD simulations directly to the EHT. That is to say, Dom just described how you might extract out or synthesize out the salient features of the simulations in terms of sort of geometric model, crescent-y type thing, and fit that directly. But why can't we just do it go straight from the numerical simulation to the data and ask what the consequence is? And we do have, I believe it's true, the largest simulation library ever assembled of black hole accretion flow simulations. So this is a magnificent resource, which I imagine we're going to mine for a very long time. And it looks like anything and everything that can happen is represented here. But as all good theorists, I live in terror of the tyranny of data. And with the EHT now, the tyranny of high-quality data. And the reason is, in these simulations, you can see there are stochastic fluctuations. There are features which are not in the large-scale flow, but they're associated with turbulence or transient elements within the emission region. And in that seizure-inducing movie, you saw many of these things whipping around. Okay, and so then if you imagine, well, we didn't see something quite as well resolved as this. This is the movie that's been setting all the expectations, which is why people say, well, it's kind of fuzzy. It's because they've been looking at these movies, so I guess we're sorry. But if we reduce that down to maybe the real number of pixels available, it's of order 20-ish pixels across the image. But nevertheless, if these fluctuations are of order 50%, and we have data that has a signal-to-noise ratio of between 10 and 100, with 20 modes on average, if you took a snapshot and randomly tried to find the one that looked like the data to within this SNR, you would need between million and I don't even know what to call it, 10 to the 25. Okay, snapshots. So that means you're going to be running simulations for a very, very long time. Not only is that impractical computationally, it's not, I think, even feasible given a large enough computer and enough time because the simulations can't keep going. Okay, so the first thing that I want to talk about is how do we solve a problem like that? How do we do model assessment in this situation where practically we would need far more models than we would ever be able to produce? And to illustrate this, I'm going to step back from black hole weather and go to the illustrious meteorologists who have been looking at problems sort of like this for a long time. This is a cloud. I hope you all recognize what it is. It has all these funny little features on it, right? If you drew a cloud, it would never look exactly like this. If you go look up at the sky today, I didn't see if it was cloudy, but maybe you would see one of these objects. Certainly this looks like some of these, and meteorologists would be able to tell me exactly what cloud that is. But of course, it doesn't statistically look exactly like any of these, right? So how do we get the same problem where we have a lot of little random features and compare it to our library, in this case of clouds, and identify that, well, it certainly looks more like this one than that. Okay? And at some level, this is a problem of answering the question, what does it mean to fit? Okay, and so, taking a step back, what we mean by that is a model that's consistent with the data up to the expectation from the random fluctuations that we are faced with. And the normal thing that we teach our undergraduates is dealing with observational errors. These are the random fluctuations characterized by our error bars. And here we have this additional term, both in the clouds and the simulations, of stochastic errors. These are random fluctuations that are present in the image associated with the random processes involved in the generation of the images. The thing that we're going to leverage is the fact that the simulations are not only giving us a characteristic image, here are average images from two different simulations, but also a characterization of the noise, a characterization of not just what a given realization of random fluctuations might be, but the distribution of them. And these can be very different. We can have some simulations which have relatively low noise. They look like their average image most of the time. And we can have simulations that look very different from their average image much of the time. Now, to move forward and be quantitative, we're going to also talk about a fitting experiment where we take a single snapshot from a GRMHD simulation, and we rotate that snapshot on the sky. We grow it out, we expand it, stretch it, or compress it, and we brighten it and dim it. Okay, so that's a very simple modification. In fact, it's far simpler than the geometric models that Dom was just talking about. But it's still a fitting procedure, and this is fit in exactly the same way that Dom talked about, just faster. And what you get from that is this position angle, a stretch factor, and an intensity renormalization. Okay, and we can do this for each one of these snapshot images. And then you can start to ask questions about how similar two things are, or how far apart they are in some sense. You know, for example, in terms of a chi-squared. If I took one simulation snapshot and I compared it to some reference snapshot in some idealized data space or degree of freedom space, I could imagine how far away is it from one or the other. And in fact, I could do this for every one of the snapshots and build up a distribution of distances. And then I can ask, is the data like one of these snapshots in comparison to my reference image? Of course, we could find it's not like our collection or our constellation of snapshots. It could be much further away than typical. Or it could be also different in a new way, in a way that's not usually very familiar, and that is it could be closer to our reference than typical of our snapshots. And these two have very straightforward interpretations, so this is just typically a bad model, but this is a model in which the noise is wrong. This is a model in which you expect larger deviations than you see typically. And to put this back into the kind of language that we teach our undergraduate lab students, this good model, just right, this is a model that might have, if we were talking about Gaussian errors, a reduced chi-squared of order 1. Okay, so it fits the distribution of distances we expect. This is a model in which the reduced chi-squared would be much bigger than 1. It's just bad. But this is the model that we don't normally encounter in undergraduate labs, where the reduced chi-squared is much less than 1. Right? In this case, it's not a measure of overfitting. It's not a demonstration that you've added too many parameters, because we haven't added parameters. It's a demonstration that the noise model's wrong. Right? And that's coming out of the simulation. So we can make this sort of comparison concrete. Here's an example of doing this with two different data quantities. So these are closure phases, the kind of thing that Andrew talked about this morning, for 3 different simulations. The blue dots are comparisons to the averaged image from the simulation. Okay, this is almost identical to the plots we saw on the previous slide. This is a good model, sort of the Goldilocks model. This is one where the data is typically different from that average image. This is one where the data is much closer to the average image than a typical snapshot. The most complicated thing about average image scoring was coming up with a name. We started off with mean image scoring, and then somebody pointed out that that spells miss. I thought, that doesn't sound very optimistic. Arithmetic mean image scoring sounds like it's just inviting people to be skeptical, a miss. So it became ACE. Okay. And you can do this not just in these 2 data directions. That's just for illustration. The way you really do this is by numerically constructing the distribution of your distance statistic, here reduced chi-squared. And here's one where it's too small, here's one where it's too big, here's one where it's just right. Okay, so Monica showed a version of this picture already. This is what happens if you apply this average image scoring to all the models in the set that we utilized. All the red ones are fails for the average image scoring, and all the green ones are passes. So it turns out it's not terribly diagnostic. I think equally important is that if you place an additional constraints that Monica described, the ancillary constraints, X-ray, luminosity, radiative efficiency, and power in the jet, then you still have about 1/3 of the models pass. So the conservative thing you can say here is, indeed, the GRMHD simulations are entirely consistent with the 2017 EHD observations. Here's 3 arbitrarily selected, well-fitting models by this measure, passing models. And from those models, we selected the best fit snapshot image. It's rotated, stretched, and rescaled to best fit the data. You can see two of these have a prominent photon ring. Looks about the same size. You can estimate to yourself about what the mass must be. But this is a third model which also fits about as well, or at least passes. And this photon ring is considerably smaller. And the reason is because we have more emission further out. And so then this brings me to the second thing I want to talk about, is trying to back out information about the underlying system from these comparisons, that is parameter estimation. One of the key benefits we have here is that we don't have to go through one of these calibration procedures, right? We are using effectively the calibration set that is employed for the crescent model fitting and ultimately will be employed for the image domain methods by fitting them directly. So again, let me just point out we have this for each snapshot or for each frame of the simulation, a rotation, a rescaling, and brightening. The rotation is just related to the orientation of the forward jet. In the simulations, we know how those two things are related by construction. The rescaling, the stretching, is related to the mass, or more properly related to the angular scale of the mass. So you can go through an exercise of fitting it as I described before and produce one of these triangle plots or posterior distributions just as a test, fitting one of these snapshot images to itself. That passes just fine. The one thing I want to point out here is these are exceedingly narrow. This is a 0.8% width on the angular size of the mass. Okay, so this is a tiny, tiny posterior. If we just focus on this panel here, which is really the angular size of the mass against position angle, and expand the range considerably. So now this was that original plot, is shown by this little dot here. And we repeat this procedure again, not fitting an image to itself, but by fitting an image to other snapshots or data generated from other frames within the simulation. This moves around. And it moves around because of those stochastic components. And in fact, if we repeat this exercise over and over again, we will have a constellation of these points moved all about. Okay? And this is just a sign that actually one frame is not necessarily a good fit to any other frame for exactly the reason highlighted at the beginning, the tyranny of data quality. Nevertheless, the distribution of these is a proxy for the final posterior. Okay, and the idea there is that, or the conceptual step there is that if we find a fit nearby, if we find a fit at some location, then nearby there is a good fit. There would be a nearby in the turbulence space. There would be some realization of the turbulence, which would be a good fit. Okay, so making a modest cut on the quality of the fits to eliminate obvious outliers, we can generate a posterior from the entire simulation that is now accounting for, in a direct sense, the stochastic fluctuations. Okay, this is sort of like putting in your random errors directly into your model instead of including the error bar in your chi-squared. Okay, notice the width of this posterior is quite a bit larger now. It went from being less than 1% to about 30%. You can apply now this procedure of taking one snapshot and comparing it to a given data set and compare it to the actual data now, not a data set produced from one of the frames in the simulation. And that's shown here for 5 different data sets, just showing the mass. So it's just showing the 1D posterior on the angular size of the mass for 5 models that are selected only by virtue of having passed the ACE criterion cut. There are 2 methods that we used for this fitting procedure. Both of them give entirely consistent results. And across these models, the results are nicely consistent as well. Okay, and there's the value that you'd get from the geometric model fitting. We can combine all of the models that fit well and generate a single posterior that's then marginalized or integrated over all the different models that we have in our library. And that's shown here. Again, we have 2 sets of triangle plots because we had 2 methods for doing this fitting. And the main point I wanted to convey is, once again, if here's the angular size coming roughly from the crescent model fits, and that fits rather nicely. So something that I think we did throughout every step of the collaboration is look for consistency between many methods, consistency between many days, consistency between bands, et cetera. That is to say, we looked for the consistency that builds confidence that the features we're studying are in the data and not in our assumptions. And that's true here as well. The masses across days and across methods are consistent with each other. And here's the second panel in the plot that Dom showed at the end of his talk. There's the geometric model fitting mass estimate. Here's the mass estimate that comes straight out of the GRMHD comparison. Okay, so very different methods, nearly identical mass estimate. For the next one, see Kazu's talk. The thing I'd like to finish on is coming back to this question of which side of the image should have been bright. One of the things that I mentioned about the simulations that they bring to the table is the relationship between the distribution of brightness in the ring and the physical structures on larger scales. And if you, there's a subset of the simulation, average simulation images shown in paper 5, and each one of them has a noticeable brightening on one side. These are all positive spin models, but I think these ones are sane and these ones are mad, and they have different electron heating models. So it's a smattering of different models, all positive spin, and they all are brightening on one side, and that's related to the direction of the forward jet, or more properly, the direction of the black hole spin. Okay, so here's a blow up of one such model. You see it's bright on the southern side, and that's because the jet's propagating that way, and the spin is pointed into the screen and projected in that direction. Now, there was the question before, what direction is M87's jet pointing? One thing also that I think is worth pointing out and remembering is that on April 9th of this year, this was the highest resolution image of M87 ever taken. This is the 3 millimeter VLBI image of M87. You can see the extended jet. It's pointing off into the west-northwest, aligned with the large-scale jet at 7 millimeters and both shorter and longer wavelengths. And this is the zoom in to the EHT. And I always think, when people complain about it being fuzzy, it's worth remembering that we went from that to this. All right? This wasn't just a small step, a quantum leap in resolution. But it's bright in the wrong direction, right? The jet's going this way. How do you explain that? Well, this was already explained by the simulations. This is the prediction. So Monica totally did not take enough credit for that. The simulations were getting this right from the get-go. And in fact, you can go back to papers Avi and I wrote, and it was the point there as well, that as soon as you have relativistic motions, the part that lights up is not necessarily the direction of the flow of the material, or of the large-scale jet. It's set by the motion within the jet. Okay, so these sorts of simulations, I think, have a key element that's validated just by the fact that it lights up in the south. And we can quibble about whether or not it's exactly in the right direction or very close to the right direction, but it didn't have to light up 90 degrees-ish away from the direction of propagation of the jet. I can't help but point out that this is interesting for a lot of reasons. Not only do we have a new measurement of the mass or an additional measurement of the mass, we also have this validation of the direction of the jet, but we also have validation of the underlying picture of jet launching, or at least strong evidence for it, the idea that magnetic fields are extracting the spin of the black hole and launching outflows. And that's a missing ingredient to an argument for the existence of horizons that relates the impact luminosity to the accretion luminosity, and in the case of M87, necessarily to the jet power. Okay, and the idea being that as material rains in, powers the jet, confines the magnetic fields which power the jet, if that material were to land on the event horizon, it would heat and shine, and the missing piece was some good reason to believe in this kind of cartoon picture that we've been talking about for some time. But now that seems to be on firmer ground. And so the expectation, had we had some surface, or had we not had an event horizon of a thermal bump associated with this impact luminosity, associated with this material raining onto whatever object we had there, is clearly missing. And evidence of absence not necessarily being absence of evidence it does look like it's hard to explain this in vanilla astrophysical terms without an event horizon. Okay, so let me just throw out my conclusions. First, quantitative cloudology is possible. We do have ways for taking these stochastic images and saying something quantitative about them. A lot of GRMHD models are consistent with what we saw. We have this intrinsically calibrated mass estimate. I think there was a concern that if the GRMHD models don't apply, this mass estimate can be wrong as well. And this position angle is related, or is similar to what we would have anticipated from the GRMHD simulations directly. Thank you.
Okay, questions for Avery? Here.
So a couple of questions. We've seen hints from our galactic center that the innermost orbits of the accretion disk don't necessarily have to line up with the large-scale disk. Could it be possible that the inner accretion flow of M87 doesn't match up with the large-scale outflow angle? And another remark.
So let me address them one at a time. So your question is essentially, why did we expect the small scale jet, the horizon scale jet, to align with the 7 millimeter or 3 millimeter jet?
Yeah, how certain are we that it does?
Yeah, I don't think we're necessarily certain that it does, right? But 3 millimeter is already getting pretty far down. So if you're going to have a substantial bend and then it coasts in one direction from then on, that's starting to have to happen quite close to the black hole. But it could happen, yeah.
Yeah, and also, if you're using chi-squared as a criterion to assess goodness of fit of images, then that's additive in a way that some pixels might contribute much more than others. Are there sometimes regions in the images that, for physical reasons, we know not to trust as much, that we could perhaps account for it?
So the chi-squared here was really a proxy for log likelihood. I'm using the same log likelihoods that Dom mentioned, and we're fitting directly to the visibility amplitudes and the closure phases.
Okay, so not to the configuration system. Okay.
Okay, maybe time for one more question while Kazu sets up.
For the simulations that fit all of the constraints as well as the imaging, can they be distinguished in terms of their 345 gigahertz images or by their year-to-year variability?
So we haven't even begun to talk about what we can do with variability. We did hear from Maciek earlier that M87 is clearly variable, and I would point out that GM over C cubed for M87 is 9 hours. Okay, so 6 days is starting to get to the point where interesting things could be said. That's something we should talk about.
Good. Let's thank Avery again. Okay, so our next speaker is Kazu Akiyama. Kazu is a Jansky Fellow and a postdoc at MIT Haystack Observatory, and he'll tell us about the mass of the black hole and future prospects.
Okay, hello everyone. My name is Kazu Akiyama from MIT Haystack Observatory. So this is the final talk of this EHT session in this conference. And I'll talk about actually one of our final products, the mass of the black hole, already actually spoken by Dom and Avery. And also I'd like to present about the future prospect of EHT observations. So now we have this brilliant images of the first ever picture actually of a black hole. So as already presented in many talks, so this is in the shadow of the black hole or photon sphere of the black hole illuminated by surrounding photon ring. So this actually size of the photon ring is a really good probe of the black hole mass. So the diameter of the shadow is purely determined by the space-time of a black hole. So for instance, for normal rotating black hole, this should have a circular shape, and its diameter is about 5.2 Schwarz radii, square root of 27. This really doesn't change even the black hole is spinning. So the minimum size is given for maximally spinning black hole seen from the spin axis. So proton view of a black hole, that gives a 4.84 Schwarzschild radii. So regardless of spin or regardless of a viewing angle of the spin, the diameter of the shadow is roughly like a 5 Schwarzschild radii plus minus 4%. So if we measure the diameter of the ring, then just divided by 5, then what we can get is the angular size of 1 Schwarzschild radii. And M87 is a very good galaxy in terms of distance measurement. We have a standard candle and also second candle, which actually provide a very accurate measurement of distance of 16.8 megaparsec. So if we multiply angular size and distance, then actually we can get a physical length of 1 Schwarzschild radii, which is solely proportional to the black hole mass. So that's why actually by just measuring the size of ring, we can actually measure the black hole mass. So Dom already presented a very beautiful, crescent model fitting. We can actually do a similar thing on using the images. So what we can do is that we can trace the ridge line of this asymmetric ring emission, and as a function of position angle, and what we can do is that we can, from the radii at the peak radii, actually we can derive the diameter and also its uncertainty. Of course, when we actually need to convert the radii to the black hole mass, then actually we need to think about a couple of effects that can actually cause a bias. The first one is, as already Dom presented, well, basically this is fitting photon ring, which should be larger than actual shadow size. So this actually provides a positive bias. And also there's another unique problem in image domain. So because the images have a limited angular resolution, so what we got is probably a kind of blurred thin ring. And as you can see, so if we blur this thin ring, then actually the ridge line of the ring is actually smaller than the real ring size. So we actually need to correct this bias effect. So what we did in paper 6 of this first M87 result is that we actually did exactly the same thing with Dom's analysis. So we used more than 100 of GRMHC simulation and made a synthetic data and just ran through the imaging pipelines and made images and actually fitting the ring diameter on the image domain. So that provides a kind of bias correction factor, and we can get a kind of bias corrected angular size of the black hole from image domain. So the result is really fantastic. So here, this is the angular size of the gravitational radii. And here, different background color indicate different days. So April 5, 6, 10, 11, and 3 points are coming from the 3 independent imaging pipelines, as Andrew already mentioned. So as you can see, that regardless of imaging pipeline or regardless of observing day, we got excellent agreement, which is, well, just incredible. And then now we have all mass measurement. So here, so the vertical axis is the black. Oh gosh, it's gone. All right. So here, so this is a black hole mass, and then previously we have so two actually black hole mass measurement. The first one is using star motion inside a sphere of gravitational inference that actually provide almost 6 billion solar masses. And another one is a gas dynamical mass, actually using gas motion inside actually sphere of the gravitational inference. So what we found is, so as already in the previous talks, so we find 6 billion solar masses from the crescent modeling, and Avery shows excellent agreement using the GRMHC model fitting. And on image domain, again, we have excellent agreement. So it turns out that M87 have 6.5 billion solar masses. By the way, this is 10 to the 40 kilograms. This is actually, actually even massive as a supermassive black hole. So what do we have learned from the all EHC results? So actually there are many results, but let me pick up just representative ones. So first of all, I believe the Einstein GL has passed a new test, namely the presence for shadow of the black hole at an extremely strong gravitational field. And we believe that this is actually strongest evidence for the presence of black hole in addition to the detection of gravitational waves from the black hole merger with LIGO. And also, Monica and Avery now actually presented that the M87 central black hole is spinning, and actually that can power the jet using the Brown-Forjanic process, actually extracting the energy of the black hole spin. Then actually Avery also pointed out that the M87 is an active galactic nucleus, and it has a jet. And finally, we confirmed that actually an AGN and jet are actually powered by a supermassive black hole. Then now, actually, we gave that in terms of mass measurement, actually stellar dynamical mass is correct, and gas dynamical measurement, it will require some calibration in future. And Maciek and Andrew actually gave excellent results that now actually we start to see a day-to-day variation on horizon scale. It's amazing in terms of the really high mass of the M87. So, what we can expect for in future? So, I actually, well, let me just insert ESV. Oh gosh, it's going. Right. So, what I actually want to emphasize is EHT is just begun. It's in the beginning. So we started observation with ALMA and more, well, roughly almost full array in 2017, but EHT is still evolving. So for instance, so we have the Greenland telescope from 2018, and also we doubled a bandwidth, which actually increasing sensitivities. And also in 2020, we'll have two new stations, NOEMA in France at Proto Debut, and also Kitt Peak Telescope in Arizona. So these two new telescopes will provide very short baselines, intermediate baselines, actually filling the UV space. So what we can expect in the near time. So for instance, one of issue actually seen in our M87 images is we know there is a jet, but we didn't see a jet. So the theory prediction or theory interpretation is, so here this is a GLMHC model, and this is actually log scale contour. So at 230 gigahertz, the jet, it becomes really optically thin and it becomes faint. So here, again, this is a linear contour images, and we really cannot see the jet emission here because it's so faint. So if we do simulations on this model with a 2017 or 2019 coverages, actually we really cannot constrain the emission from the jet. So if we extend the field of view, then what we will see is a really asymmetric noise, and we really cannot see jet. But 2020, we will have two new stations, Kitt Peak and also NOEMA, and actually that provide a lot of short baselines here, and hopefully we can actually start to grasp the emission from the jet. So in the new time, actually we can actually start to study the relation of the horizon scale images like a shadow and actually jet launching lesion, which is exciting. So far we actually have focused on M87, but we also actually have another excellent target, Sagittarius star. So I believe most of us in this conference is now really focusing on M87, but we have another excellent target, Sagittarius star. By the way, this is my most favorite tweet about EHT results made by Bestie Mills in Brandeis. She's a very famous researcher for the Galactic Center. But anyway, we actually also want to emphasize that we still love Sagittarius star. So the reason why we are taking so long time to analyze Sagittarius star is actually it's coming from the source character. So the mass of Sagittarius star is 4 million solar masses, which is 1,000 times smaller than M87. And we already see day-to-day variation in M87, and actually that is happening on minute scale for Sagittarius star. So for instance, this is a very beautiful movie by Avery and Avery Love in 26 paper. So actually everything is changing within like a time scale of 20 minutes. And if we actually make images using some new movie reconstruction techniques, by the way, so we are using kind of agnostic flyer. We really didn't force, for instance, the source size for this particular reconstructions. So if we use some a very weakly informed prior for imaging, then we can actually still capture some motion of hotspot here, but we also see some artifacts. So that's why we really need to be very careful about imaging analysis for Sagittarius star, even more actually careful than M87. And if we have more stations, then actually we start to actually accurately grasp the dynamical feature of Sagittarius star, even without strong prior information about the source structure. So now actually we are actually working hard for Sagittarius star, and hopefully we can get the first images very soon. So, and also now we are in the beginning stage of the next decade, starting from 2020. So I believe there are two key parameters for a potential extension of the EHT. So first one is a dynamic range of images or sort of imaging sensitivities. So current EHT images are highly limited by its spatial frequency coverages. So basically, we are missing a lot of structural information because we have a just limited number of stations, and we can get a just really limited number of Fourier component. So obvious solution is we should have more ground telescopes, and now we are planning to have the second generation EHT, so-called EHT2 so far. And this is a kind of more long-range target, long-term target, but maybe we potentially have a satellite in the space at low Earth orbit, which is actually really rotating fast. So this will actually provide much denser coverages of observations that actually lead to a really booming sensitivity to the much fainter or extended emission structures. And for Sagittarius star, it's really crucial because it will probably provide a better fidelity of reconstructing dynamical features. Potentially, we can actually also have a 345 gigahertz observation, and we can combine two frequency and actually getting much higher angular resolutions. So let me show just quick examples. So this is actually one of the planned array of EHT2. So here, the black lines are from the current EHT array, and red lines are coming from the planned array of EHT2. So EHT2 have like 20 stations, and actually fitting a lot of gaps. You can see actually really good coverages. And also, so blue lines are for 345 gigahertz, which is roughly 1.5 times larger. In terms of the Fourier space, giving 1.5 finer the better angular resolutions. And of course, we can maybe combine the two frequency using a multi-frequency synthesis, and we can get maybe deeper and higher angular resolution images. And also, this is really stunning simulation by Daniel Plombo. So if we just have one station at the low Earth orbit, for instance, the orbit of the International Space Station, then actually it's really rotating fast. It can quickly fill in the UV space of our observations in a symmetric way. This is really fantastic. So for instance, so we already show what the EHT 2020 images would be. But for instance, for EHT2, we can get this kind of images, almost like it's just simulation. So we can really make a dynamical movie of jet launching with better angularization and deeper image fidelity with EHT2. And also, the Sagittarius star images are really improved, again, even without any source structure assumption during the imaging process. So it's providing actually much better fidelity than at the current array. And also, if we have just low Earth orbit satellite, just single low Earth orbit satellite is actually the game changer. It's really enhancing the image fidelity of the dynamical image reconstruction of Sagittarius star. And then also another important parameter is actually angular resolution. Maybe we can, the current EHT angular resolution is limited by just the size of this planet. So if we extend, so for instance, our array to the more actually larger orbit, then actually we can actually get much higher angular resolution. Maybe this is useful to get the accurate measurement of the shadow shape for the M87 or Sagittarius star. or capturing much finer structures, or even we can actually start to see a horizon scale structure of other supermassive black hole in other galaxies. So this is just simple simple example of how spatial coverage could be just by adding a single or maybe couple of space stations. So these are coming from the mid-Earth orbit, where actually GPS satellites are, and also geosynchronous orbit. So now you can see Earth-bounded ground stations distribution here, but actually we can actually extend our angular resolution by factor of 3 or 4. And this is at 1.3 millimeter, and it's actually reaching at the spatial fringe spacing corresponding to the 1 Schwarz radii. So actually we can now actually get into the 1 Schwarz radii, or actually much finer scales at 345 gigahertz if we actually launch a satellite on the mid-Earth orbit or geosynchronous orbit. So this is just a kind of toy model. So this is just like a GLMHC simulation at much higher accretion rate, maybe expected for flaring state. So in that case, sometimes we may see a very thickening coming from the inner circular stable orbit of accretion flow. This really cannot, so it has a kind of double-ring-like shape, but we really cannot see the double-ring structure with a ground-based array, but with space, actually we actually started to see this kind of very tiny feature in images. Or if we go to the 345 gigahertz, the angular resolution is actually much better. So it's just the image reconstruction is like just the original figure. So I don't want to actually emphasize this particular model, but actually this is a good demonstration for actually how we can improve the angular resolution if we extend EHT to this space. And also for other sources, so Dom actually made a really nice figure here. So here is the 230 gigahertz flux density as a function of the shadow diameter of the black hole for the nearby supermassive black holes. So here you can see the lines. This is the angular size of the ground observations, and here is a typical space VI angular resolutions. So, here you can see the Sagittarius star and M87, but actually there are some radio blide and also large angular size supermassive black holes in our nearby universe. So one actually promising source is the M104. It's known as the Sombrero galaxy. It's a low luminosity AGN, and radio blide have a jet. And also IC 1459 is a radio galaxy in the southern hemisphere. M84 is an elliptical galaxy in the Bargo cluster, so it's actually very close to the M87. So for instance, if we can extend the EHT to MEO satellite, then actually we start to actually capture if there is a shadow in outer galaxies. So we can actually we can actually look at horizon scale structure of black holes in the nearby universe. Anyway, so I want to stop here. So I just want to emphasize that EHT is at the beginning stage yet. We already got exciting results, but EHT is still evolving. And in a near time scales, we will work on Sagittarius star and also M87 parametry, which is actually talked by Monica briefly. And we doubled bandwidth in 2018, actually achieving higher sensitivity, and also maybe we can do a Faraday rotation imaging. We'll add 3 new stations in the next few years, going to higher frequency. And 2020s are actually the era of expanding EHT in maybe ground or in space. So I want to stop here. Thank you very much for listening.
Okay, questions for Kazu? Yeah.
You showed an image of the diameter of the shadow that was very wobbly, and you took measurements throughout a week. Does that, not this image, the other one that then you averaged, the question is, does that change during the different days that you observed, or is that a constant?
That's a great question. So let me show some slide here. So I forgot if Andres showed this slide, but so here is the diameter. Well, this is before bias corrections.
Yeah.
So this is just purely determined by that ridge line of the ring. And here different colors are coming from the different imaging pipelines. And for April 5th, 6th, 10, 11th, so different days. So you can actually see that a diameter really doesn't change. It's actually around the 40 microarcsecond, and regardless of imaging pipelines and regardless of day.
Okay. Because when you say bias, what's the name you gave?
Sure.
So the question is the following: how do you know there's one object there? Could you have several objects that are generating a shadow like that?
Sorry, I don't get that. Is that do you mean
say a supermassive black hole with sprinkled 1,000 more smaller black holes, or 2 black holes generating one jet? How do you know that your bias is just thinking that there's one object there?
Yeah, so that's an interesting question. So I think we actually what we tried is a kind of Occam's razors approach. We just assume the most simple solution, just having just single black hole.
Oh, I agree. Yeah.
Yeah, and it can just explain everything and doesn't require additional, for instance, additional black hole, for instance. So I think it's a really interesting question. Yeah, and then also, as far as I saw talk about binary black hole in this conference, the shadow shape is actually not circular, but what we got is a really circular shape of the shadow. So it's already actually constraining a lot for the presence of the binary black hole.
The size is 6 billion solar masses. So I think one thing we're pretty sure of is there's probably not 2 6 billion solar mass particles.
Sorry, can you say that louder? I didn't hear. You're sure?
There aren't 2 6 billion solar mass black holes.
Yeah, well,
Right?
yeah, no.
So then you have to have some strange, very fortunate alignment or something.
No, but it's worse than that. If there were 2 black holes separated roughly by radius, they would come together within much shorter time than the age of the universe. So, I mean, we have to be extremely lucky, and if we look next year, there might not be.
Well, but the shadow is not very smooth. It's not very round, correct?
Well, it's pretty round. It's as round
Well,
as
yeah, you can be very biased.
Okay, well,
Well,
I think we should continue this discussion offline. And we need to move on, so let's thank Kazu again. Okay, but don't leave your seats yet. We have one quick addition, which is Dennis Gray is going to just walk us through a couple slides on surveys. And
Great. I promised just to steal about 3 minutes of your break time. I'm Dennis Gray, and I'm connected with the BHI in a program evaluation role. I've been doing research. I'm a social scientist. I've been doing research for about 30 years on large multidisciplinary centers, institutes, trying to understand how they operate, how they can operate most effectively, particularly where there's a goal of interdisciplinary kind of research. So I've been working with BHIs from actually the launch. And what I wanted to do is just talk to you briefly about some data collection we're doing. It's not the kind of data collection you're involved in, but when the BHI proposal was submitted, The overriding goal that was provided to the Templeton Foundation was to achieve superior science through a multidisciplinary approach to black hole research. When that goal was formulated for the initiative, the BHI said, we're not only going to try to do that, but we're going to try to measure and document that we're doing that in various different ways. And the implications of that is you all are a part of a big experiment. So this is not just science, but this is science on a grand scale, trying to bring people together across different disciplines. And so just trying to unpack this, this, in a sense, is the vision of the way the field of people working on black hole research existed prior to the Templeton Foundation. A lot of people in disciplines doing very good work, but basically sort of operating as silos. And I added this a combination. I've been, as a social scientist, I've been amazed as I've been at the meetings. We're still talking about Albert Einstein, general relativity. There's a quote from Einstein about how important combinatorial play is in productive thought, getting people together across disciplines. This is a very complex graphic, but this is the image. This is the theory of change that the PIs involved in BHI presented to Templeton about what would happen with the field if they were willing to fund this kind of initiative. The disciplines would work together addressing really important questions. They would weave together communities that previously had not talked as much as they should. And I put a little graphic down at the very bottom of this. That's you. Those are the people who have sort of been pulled in, I guess, through this black hole research to be part of this community. So with that as just a background, the question that I've been trying to deal with is, how do we know if the collaborative change has happened? How do we know that this kind of crosstalk? These meetings are a very important part of what the BHI have been trying to do. And so we're going to need your help. And basically all I'm doing is making a pitch to you to fill out a survey. We need to find out how this meeting went and also what your thoughts and observations are about how BHI are operating. And what I will tell you is this is the third meeting. We've done this in the past two. And the feedback that has come in from you and your colleagues have been taken very seriously. There have been changes made in the program that you're being able to take advantage of now, which came about from people saying, hey, let's be more integrative in the disciplines on a single session. So those comments have been listened to. So with that, one last slide, I have a request. Tomorrow, you're going to get an email message sometime in the morning, and it's going to be a simple message saying you were registered for the BHI conference. We'd like your input. You need to click on that, and I'll make you 3 promises. It's a very short questionnaire. It should take no more than 5 minutes of your time. From past practice, the BHI leadership have taken the results very seriously and used it to make changes to the future. And as an extra incentive, if the intrinsic rewards aren't enough, if you fill out the questionnaire and you put, the last question is there a charity that you would like to make a donation to of $100? If you fill that in after I get the surveys, I will pull one survey and make a $100 donation to whatever charity was named in that. So you can do good for the center and potentially do good for whatever survey you mentioned. And with that, my guess is everybody would like to have a productive break and interact with everybody in the room. So thank you very much.
Great. Okay, so we have a coffee break now.
final only panel of the day. And we're going to go from now till just before 6 o'clock we have dinner. So that's the plan. Oh, until 5, right. Okay,
It's all
I
relative.
can count up to 4 really reliably. So what I thought I'd like to start by asking the panel, in light of all these wonderful talks we've just had on the EHT, what you think we might do to help facilitate contacts between the EHT and the various other specialties that have been represented here, theory, mathematics of black holes, questions of multi-wavelength formation of supermassive black holes, and so on. Are there mechanisms of collaboration that might facilitate the kind of exchange that we've been hoping for? I'm not going to call on you, so one of you wants to speak.
I'll say a couple of words. Is this on? Yeah. You can hear me? Well, I think it's a great question. This is all very new, right? I mean, April 10th, we have this image of a black hole. We never had one before. But now that people are beginning to wrap their heads around it, I think that, dare I say it, that the Black Hole Initiative is the right place to foster these kinds of connections. We're already making them. Where's Andy Strominger? Andy, where is he? There he is. There's Andy. Yeah. Andy, bravo, Andy. Bravo.
Just answer the question, Andy.
Yeah. We elected you to all the committees, Andy. So Andy and his students, Alex Lubsaska and others are working now on conformal field theoretic approaches to understanding high-spin black holes that may be applicable to M87. And as we think about the next stage of the EHT, I think Kazu called it EHT2 aspirationally, which is one more than EHT1. We're thinking about investing a lot more in it. And you need to do that in order to take it to the next level, to go from still images to making movies. If you're going to launch something into space, pretty soon you're talking real dollars. And if you're going to do something like that, you really need to trace the science goals through to the nuts and bolts that you put together. It's called the science traceability matrix. And I think that that's going to involve everybody. It's going to involve mathematicians, theorists, astronomers, physicists, everybody. And if we can make a really interesting science case, then we can do some quite remarkable things technically in the future and answer some fundamental questions.
Other thoughts? Katie? Monica?
Well, I think this is already EHT collaboration is great. I mean, this is very close collaboration between theories and observers. This doesn't happen so often just in astrophysics itself. So, yeah.
I really, for example, Monica, I really think that the simulations are going to take off. I mean, I think that we're going to start doing microphysics in those simulations and see if we can observe those kinds of phenomena. So.
Yeah, definitely. It's very constraining now. Finally, theories are constrained somehow. So.
But I also think like the example you gave in your talk of how the large-scale jet structure really also helps to rule out certain models. I mean, that also required, apart from just the EHT, right, like other multi-wavelength data. And I guess that's not necessarily philosophy and stuff, but it's still bringing together people from different communities and different expertises to try to, learn more about what we're looking at.
When you, Monica, when you spoke about the sane and the mad models, and I mean that's come up again in several of the talks, and I know Ramesh has been working on these. This is a theme that we're trying to differentiate between those two kinds of models. Do you think there's a strategy forward as to how we could make the decision between those two?
Yes, of course. The next step is, of course, to do, to look at the polarization of this ring, and that would be very strong constraint on the theory, because then, you just don't see the total intensity. We can also map the geometry of the magnetic field around the horizon. So that, I think, that's the key, to choose which physical scenario is realized in nature. And I made this joke at the beginning that, we didn't have to make any observations, but that was just a joke, of course.
Yeah.
Careful with
Very
those jokes.
silly joke. I wouldn't be here if we,
I didn't laugh too much at that.
It was a bad joke, okay.
Ramesh, do you have where would you like to go next with the simulations? Do you have an idea now that the observations exist and you've got a long train of extremely sophisticated simulations that you've been doing over the years in preparation for this moment? Do you have a sense of where it goes from here?
I think, yes. Now, more than, say, yesterday, after listening to Kazu's talk and seeing, how far the dream could go, if we could get additional stations on the Earth and spacecraft and the greater bandwidth, Shep, so that you get the signal to noise. Some of the pictures that Kazu showed those are really kind of simulated reconstructions of images from simulated data. Those are beginning to look really detailed. And I think at that point, we are going to start making fantastic comparisons between what our simulations, based on our knowledge of the astrophysics of this object, how does that relate to the real object? And I think we are going to start understanding not just the strength of the magnetic field, which is the sane versus mad, but the geometry. We're going to start seeing, I think, certainly we'll measure the black hole spin. That's going to be extremely exciting. We're probably going to start seeing how the jet is spinning, because the spin of the black hole we think is what drives the jet. We should be able to start seeing the rotation of those magnetic field lines in the space-time. What the disk will show, I don't know, but I have a feeling we're going to really start microscopic, right? That's what I think Shep said. We're going to really start seeing into the insides of both the accretion disk and the jet, something that only people had been dreaming of, and I too didn't know how quickly we will reach there, given that the one image we've made so far is, we've got 20 independent elements across the image. It's one snapshot. That's not enough to say much. But when you think of where we can go in the future with the improved technology, if you can find the money for it, I think it's going to be fantastic. So as far as astrophysics is concerned, if we can get the funds invested into this direction of research, the rewards are going to be amazing. But I'm personally interested in what the audience has got to say on the other directions, right? How do we go beyond the astrophysics, which is what, at least I can understand most easily? How can we start testing non-GR models? How can we start testing, I don't know, quantum? We don't expect really at this scale, but maybe something. I think, there are probably things that we haven't thought about that could be done if only we had the kind of quality of data that is doable. And then I think it's going to get really interesting.
Yeah, I would just add to that. I like this idea of a global science case that merges all the disciplines here in the BHI, and as Monica said, all the representatives across the Event Horizon Telescope. But even beyond that, I think the multi-wavelength component is really interesting. Because as I think we've seen today, it's the jet power, which you get not from really the EHT, but from X-ray and from larger scale observations that show the whole collimated jet, that cleave these degeneracies on spin primarily. And so as we think expansively about the EHT and the next steps, I think we have to think about a panchromatic approach, where we talk with our X-ray colleagues and gamma ray colleagues and TeV colleagues and try to figure out what the best way to attack the big questions are from many different angles.
Michael, you've been thinking a lot about the scientific questions that you could pose around for instance, as we go towards the center of the galaxy, and in addition to M87, what kinds of things would you most like to attack with these, assuming that we do get through better bandwidth, frequency oscillation back and forth between 345 and 230 and additional stations? What opens up that you would most like to know?
Well, I think there are two real limitations with M87, and they work to our advantage currently. One is that it's a big black hole, so things are slow. And what this means is that we see maybe one high-energy flare a year, and maybe we observe a few dynamical timescales, and it will just take a long time to assimilate information. And the other thing about M87 is that we're looking down the barrel of a jet. So we're probably looking down the barrel of a black hole. And so any theory of gravity you can imagine, you have a symmetry axis there, and you're going to see a round shadow. So it's very hard to access things like the spin of the black hole. It's very hard to test theories of GR. We don't have resolved stellar orbits. We don't have all of these complementary measurements that we have in the galactic center. So, to me, the galactic center is where everything's going to open up, where we know the mass and distance of the black hole perfectly, to better than 1%. And if we can measure the diameter as well as we did for M87, we could read the spin off that image. Or we can immediately test whether GR is violated. We are going to see things evolve on timescales of minutes. So, to me, the dream is this facility that's like watching the sun, right? And you're watching this living, dynamical system, and you're watching eruptions, coronal mass ejections. You have a whole suite of instruments all in pursuit of this perfect, ideal system that's sitting right in front of us. So what I really see is this future of just monitoring the galactic center and using this as the perfect testbed of theories of black hole accretion and outflow. But getting there requires so much, right? We have to develop a common language between all these different fields. It's not that we're just uniting astronomy and physics and philosophy. We're all quite specialized, even within our own disciplines. And so, I think it's going to be a long road and needs meetings like this, where we're waving our arms around and talking about jet directions and just breaking it down for each other. But this is a multi-decade project that we're just seeing the beginning of now.
And Katie, for over the last years, you've thought and added hugely to our understanding about how to use algorithms and thinking about actually making these images. As you look forward towards the next, taking into account what we've learned through the experience of M87 and changes over the days that we've been looking at it, but thinking about this much faster, quickly evolving system at the center of the galaxy, what are there directions that you see as most promising in imaging algorithms, and what you'd like to see developed or you'd like to work on?
Yeah, I think there's, as Michael talked about, I think there's a lot of science cases where we have to develop new algorithms to try to get at them, to try to get at the answers to those questions. So as an example, as Michael was talking about, the fact that Sagittarius A star is evolving on the timescale of minutes means that we can't just use the algorithms that we developed for M87 any longer, because those assume that over the course of a night you have a static image. Whereas the measurements that we would see for Sagittarius A star, every measurement is basically coming from a different snapshot of a movie. So how do we then combine this information together to get something useful out of it? And I think there's also, Michael was talking about, how do we connect? I think you were talking about how do you connect it to the jet for M87, and that requires a much better dynamic range than we have right now. So how do we access a larger dynamic range? And I think at the core, the Event Horizon Telescope is a computational telescope, and that makes it, it is by definition a very interdisciplinary project that has required the expertise of many different areas, from theory to computation to instrumentation, and even philosophy, actually, to get the results that we had. Because, for instance, questions like, what does it mean to have a single image? How do we present to the world a single image that we believe and that is to the confidence that we believe it? And how do we go about the process of making sure that we don't add additional bias into the images that we make? These have involved many different kind of areas of expertise to get at the result that we presented in April.
And Lindy, one of the things that I think is very striking at this meeting, although sometimes was lost in the immediate aftermath of the announcement, was how the data is handled and what it means. The months and months or years of work that went into getting data that you could really count on. As we expand this network, we have this network that basically, the extraordinary thing about this project at the level of the telescopes is that they were all there. I mean, it was combining. I mean, Shep, you and your colleagues for long before I was involved were working to coordinate this, which is a political,
nightmare.
You said it, but you had to.
You were searching for that word.
I was searching for that word. The coin of the realm is time on the sky, and you're asking all these telescopes to give it to us all at the same time. But it didn't involve building, $200 million telescopes. It was using the ones that were there. And now, as we turn to expand, if this network grows the way we hope to do, maybe space, but in the more short, medium term, these additional telescopes that would be added to the network, are there lessons from the experience of the corrections and data and data preparation that you would want to see in place in the next round that are created by the data-intensive study of the center of the galaxy, for instance, with its rapidly changing phenomena?
Well, yeah, I think there are lessons, but I think they've already somehow been implemented for the HT, right? The HT does use heterogeneous telescopes all over the world, but has installed rather standardized equipment at those telescopes. So we already benefit from that process quite a bit. It is really interesting to think about how the EHT is going to expand with more telescopes. There's a benefit to that. There's more data to process, a lot more data to process. But on the flip side, you have many more measurements than systematics. The number of systematics goes with the number of telescopes. The number of measurements goes as a square of the number of telescopes. So the problem, in a sense, becomes easier, more interesting, and you can do more as the array gets larger. And I think as the telescope array grows, we'll be able to move the problem of calibration from just sort of push button, do these sort of standard reduction things, to making that modeling of the instrument sort of a living part of the modeling process along with source modeling. So we're really talking about folding all that into a scientific framework where we're solving for the image, solving for the instrument in a way that really tells us what our measurements mean.
I thought we could open it up and have a discussion also, including all of you who are our collaborators as well as colleagues. And I wondered if there's some ideas that people have for mechanisms or forms of lines of collaboration between the EHT and other specialties.
Actually, I don't have a suggestion right now, but the question would be, I guess, more appropriate is how one thing is the Black Hole Initiative, the other one is the EHT group, but it's a much larger community out there. I mean, there's so many people you can fit in this room. So the question is, what sort of mechanisms are you thinking to engage the community? Just a simple example, so LIGO has put out the data and some of the analysis tools. So the earlier you can make that decision and tell the rest of the world what will be there, will engage people to do one thing or another. Because things that might not be priorities for you, especially crazy ideas that come from the woodwork of some crazy theoretician that want to go and test something in particular, you would not be a priority for you, but it might be something you would want to give it a try, that someone will go and try and engage that way.
We definitely are interested in that. Who would like to, you want to,
I can answer this because, this is something that I mentioned at the end of my talk, that, we also make this data public. It's public, it's on a web page, and not only just the data that has been, underlying underneath this image, but we also release the scripts that has been, written to make these images. So right now, everybody can make their own image of a black hole, right? But the point is that, this data is out, and whoever has now, alternative theory of gravity or something, you can just download this data and test your model. So this it's already happening, and yeah.
I think
It's just free to use.
Well,
just citation, right? But it's free to use, this data.
Yeah, so Monica's exactly right. Whenever we publish, the first thing we do is make available, or our plan is to make available all the data, and as Monica said, the scripts. We were doing that for a couple of reasons. One, it's just standard practice, but also that we feel it's the fastest way to gain acceptance across the broad community, to give people everything they need to replicate the results that are in the papers. But beyond that, we're moving now to a new kind of framework for the EHT meetings. So because some of the data will always be proprietary, probably every 6 months or every year we'll have a closed meeting where we get together to see what we're going to do with the data and how we're going to analyze it. But I would personally like to move to a model where once a year we have an open meeting, where that everybody can apply and come and give talks and discuss the latest results that are open and help at that meeting decide what the future directions are going to be. And we're also planning on going to the AAS for a special session. And of course, we'd recommend everybody come to that, and we can have an open part of that in which we take suggestions. And I'm sure there'll be meetings around the world at various different places.
Yes, Roger.
I'd like to inject a note of friendly skepticism, if I may. What does it mean you're sharing the data? Because when you give talks, you guys, you show us these great stacks of disks filled with data that only people who own the disks get access to. So what data are you actually releasing to the public?
So, Lindy, do you want to describe the data set?
Yeah, so we are still new at this, right? It is our first result, our first set of public data release. So what we shared was post-calibration, basically what we passed the imaging and modeling teams, almost exactly the same data that they used to make their images. So people could run the same modeling type of searches. They could do their own parameter search. They could, measure the shadow diameter or make an image. But yeah, we do not have the raw data to share. We actually don't necessarily keep that ourselves forever, right? The disks are recycled. At some point, probably I think the correlator output is meant to be archived publicly after some amount of proprietary period.
And what sort of data volume is this?
So we're talking about the terabyte level data volume.
But the data that we have for imaging is on the megabyte level, so you can just email it. And I think that where is Kazu? I remember Kazu shared a result that maybe colleagues of his in Japan who weren't part of the EHT have already started making their own images from the data. So there are other people who are taking this data and making images with their own software with it already.
Yeah, on laptops, you don't really need a lot to do that. Right?
Yeah, I want to point out that, this morning I went to ADS, and there are now, I think, 27 papers that cite the EHT results, right? And that's in like 1 month. It's not bad. I would have expected more. A little disappointment, tiny bit. What's that? Well, no, but we're talking the academic stuff now. But what's that? It takes time. Well, okay, I'll note. Okay, now Avi, your paper just came out on the archive on the EHT results. I was disappointed that you didn't get in there faster, right? I thought you'd be number 1, but I think you were number 25 or something like that. But the point is that people are now beginning to use these results in data, and it'll take time.
I'm curious about the publishing model. Y'all published all 6 papers in AppJ Letters, and you didn't put anything on the archive. Why was that?
Am I answering this one?
Sure.
All right, Eric. So a very short answer. I actually got an email today from the head of the publication working group, and we're addressing this immediately. However, one of the reasons we were slow to do that is because we opted for a completely open access model for AppJ. So the papers are freely available to everyone at that website. There's no paywall, there's absolutely nothing. So you go to the AppJ site, you get the papers. If that hadn't happened, we would have immediately put them on the archive.
Yeah, I think I'll add one thing to that. There was also a practical problem. Namely, after all the refereeing was done, there were lots of changes to the manuscripts. And basically the authors, the people who were in charge of writing the papers, they basically said they couldn't possibly make those changes in their own tech documents in time for the press conference. The whole time scale was very compressed, and changes were large and many. And it was just impractical to make an exact copy of what was going to appear in print and put it on the archives before or on the day of the press conference.
I mean, I just want one other thing, which is that we had, so that although they're called letters, these are the longest letters I've I've ever seen. And we had, I think there are 200 or so pages of published journal papers that came out at 9:07 a.m. On April 10th. And that was also coordinated with a whole series of announcements around the world that would give equal possibilities to each of the different major sectors of the experiment. There was of the groups that were in Europe and in the United States, but also in China and Japan, and I think there were a total of 6.
South America,
Mexico.
And at Santiago, and so all of these, there was a coordination that I don't think is going to be true in quite the same way for every new development in the EHT. So that was part of the effort, was to get publication, open access, multiple representations of the work in many places, the image availability, and to do it all at the same minute. So that was another practical side of the
Piece of cake.
piece of cake. What could go wrong? Sorry, Avi?
Just wanted to encourage also lateral thinking. So in addition to shadows of black holes, there might be other uses for the Event Horizon Telescope that could be very exciting. Just to give one example, at a cosmological distance, if there is a black hole binary and at least one member of the binary emits at millimeter wavelength, you can actually resolve the motion of the center of emission, center of light. And that would be another way to test general relativity, because it really depends on how tight the binary is, and in a way it's a tool that either will identify the progenitors of LISA gravitational wave sources, or will be one of those gravitational wave sources. And so perhaps, I mean, I don't know if you have those discussions among the team members, but it might be useful to also think about other uses of the telescope array. Have you had those?
A couple of things. One is the most likely supermassive black hole binary is probably OJ287, which the EHT has observed annually for the last decade. It's one of our primary targets. Another possible binary supermassive black hole is 3C273, which is also, M87 is 3C274. So they're close in the sky. It's a good calibrator for M87. We observe it almost every year. So there are a lot of these targets that we're observing, but in addition to that, the EHT is also open. Anyone can propose to use it. So every April at the ALMA deadline, people can put in proposals, and I think we would be delighted to see other use cases take off, even speculative ones, and just start to think about what else is possible.
Delighted?
I would be delighted.
Daniel, I think Dan, and there's some other questions over that way.
Okay, so my question is very short, and maybe you're not allowed to answer it, but why M87 first? Why is that the one that, you know, it's not necessarily what people were expecting? Is there a physics answer to that, or is it sociology?
Oh, well, I think you heard the answer today very, very clearly. I think maybe Kazu mentioned this in his talk and others. It's the time scale. So it's just much easier to image M87 because it's static on the sky during an Earth rotation, because the VLBI requires Earth rotation aperture synthesis. We fill in the Earth-sized virtual mirror by letting the Earth rotate, and the source is static during that time. Whereas for Sagittarius star, GM over C cubed is 20 seconds. So it's changing very, very rapidly. And then there was a little bit of a sociology aspect of it too, because as soon as we began to image them both, but when the image of M87 began to come into focus, we decided we would redirect all of our firepower on that just by fiat, so we get that out, and then go back to Sagittarius star. So it was a little bit of both.
But a minute in the life of Sagittarius A is like a day in the life of M87. So it's going to be a harder technical problem, but one that has the promise of all sorts of new things, like these weird flares and figuring out what they are.
And movies.
And movies. To understand these time variability questions could lead to great new, both astrophysical and physical phenomena that would be of great interest. Yeah, sure. Yeah, while you're there.
Yes, I was just interested in suggesting that you expand the interdisciplinary approach to include engineering and industry, and if you've had any thoughts about that.
I think one of you two should address that.
My allotted time is up.
Michael?
So I didn't quite follow this.
Industry and engineering, how might they join us in future work?
So I mean, everything we're doing here is at the bleeding edge, right? We're pushing all the technology that we can. So this is the fast samplers, the incredibly high data volumes to process, processing them efficiently so that we can correlate all the data and reduce it down from petabytes to megabytes in a short amount of time. There's also a lot of development on receiver technologies at the telescopes to improve their sensitivities. So I think some of these have really natural industry connections. So there are new partnerships that we're making with Google, and also possibilities of changes in the paradigms of how we actually take the data from the telescope to the correlator. So maybe instead of recording on a disk packs, maybe we're transmitting it over optical fibers. Or maybe we're beaming it up and up to an orbiter and then back down using laser comm. So all of these, I think they link really naturally with a lot of technological prioritizations that are ongoing in other industries, and they're things that the EHT will really benefit from.
Also, I want to mention Daniel Palumbo, who is running around with the microphone. He also ran a large number. So if you want to take the data that we have online and make an image, it takes a minute with the script that we have. It's really quite fast once you have a script. For some of the methods, some methods take longer. But we wanted to look at, for instance, on the imaging side, what were the variations you have depending on the model choices that you make in imaging. And so we, for instance, used Google Cloud to run hundreds of thousands of imaging at the same time in a reasonable amount of time, like over a night. So Daniel worked on using the cloud resources to parallelize, for instance, the imaging results so that we could analyze huge amounts, hundreds and thousands of images with different modeling choices. And that was really essential in understanding our uncertainty in different features of the image. So that's a different side of engineering and technology, but I think also a very important side that we leveraged.
Roger, back to your question. Even storing 5 or 6 petabytes of data, archiving it for a couple of years is not super cheap. And these hard drives, turn out, don't like to go up to mountains. You need helium-based ones. If they're spinning disks, there's not enough air up there to spin safely, so you need to. So these things that seem like they shouldn't be.
Yeah. Well, I think, Lindy, did you show the Moore's Law plot?
I didn't give a presentation today, but
who showed that today? No,
Jonathan.
Jonathan, where's Jonathan? Jonathan did. So another answer to your question is that one of the things that's made the EHT possible is hooking our cart to the Moore's Law bandwagon. And we've kept up with Moore's Law over 20 years. There are very few science projects which can make that claim. They're tracking Moore's Law. And it's the bandwidth that's really gotten us the sensitivity, as someone said earlier, to make these detections of faint sources. And now as we broaden the scope and start to think about purposefully placing new telescopes at ideal locations to fill out that virtual lens, we need to partner with industry, with new telescope makers or going into space to figure out how we can unfurl things with micron accuracy in space, things like that. And it's part and parcel of the direction we're going. I think it's very important.
I think there's a question back here.
That GM over C cubed sets some sort of causality-based timescale, but that can be thought of as a minimum timescale, and there could be processes that occur on larger timescales. So is there a prospect of separating out the longer timescale parts of the variation from shorter timescales? And also, can we take simulations and take time averages as some sort of characteristic, basic shape of what we'd expect, and if the individual snapshots and simulations don't deviate very much from time average, then is there some way we could try to assess what are the most permanent discrete features in the images versus what are the most variable ones?
So I mean, I think M87 is a nice test case for this. So we have one time scale, which is the time of an observation. So we're pointed at the sky, we're watching this thing, and we're seeing within a single gravitational time scale is the thing varying. And we see it's not. Right? All of the variation is just intrinsic structure, that the Earth is rotating and our baselines are evolving, but the source is frozen on the sky. So then next is we sample observations over about a week. And hopefully that'll be pushed longer in the future. And that's more like an orbital timescale at the innermost orbits. And then another thing is, we come back and we observe these things year after year after year. So that's a much longer timescale, sort of an accretion inflow timescale or something. So I think we actually have access to all of these different timescales in a very, our instrument's really well matched to the timescales of interest.
But I think the galactic center will be better. Because let us say the fastest time scale is some fraction of an hour. And a given observational campaign, let us say, is a week in April each year, and a week. So let's say you can observe for 7 days, many hours each day. So you will get all the time scales from fraction of an hour up to maybe 10 or 12 hours in a day. And then you come back the next day, so up to a week, you can kind of sample those time scales. But then there'll be a gap, because probably your next observing run will be a year later. So then, you can try and study what happens on year time scales. But my guess is that there will already be enough information on how variability power varies as a function of frequency over a couple of decades, or maybe even 3 decades of time scales, just from such A-star data. But it's all going to depend on the ability to make reliable images of this highly variable source. Making movies when the source is bubbling away, even while the Earth is rotating. So that's going to require all the new techniques that Katie talked about. And in fact, Katie and Michael have already developed some methods. I'm sure we can do a lot better. But assuming we can do all that, I think we will have that kind of information. You also asked about the simulations. There, the information is already there. Almost everyone who runs a simulation goes and also calculates power spectra, variability, look at images. You saw lots of movies today, right? They're all showing how things vary as a function of time in the simulated models.
And in the simulations, at least ones I've done, the snapshots look quite a bit like hourly time scales average over many time slices. So we could be lucky that over a certain time scale or way of fitting, the image looks roughly stationary.
That's if you have very, very periodic motion, right? But I guess, and this is why it's important that we connect with theory to figure out, okay, how periodic is it in different situations? So if you, for instance, had a hot spot just rotating around perfectly in a period, then yeah, I think you could average in a smart way to remove variations and just do some sort of smart static imaging. But if you have things coming in and out and it's not evolving perfectly periodically, then you have to consider that. Another thing is you might be able to learn about variations from not just imaging, but looking at, for instance, these closure phases people have been talking about and the variations you see over them over the course of a night. So as your closure phases tell you about the structure in the image, right? And as the Earth is rotating, they're going to carve out slightly different areas of the frequency plane, but you would expect that the variations wouldn't be faster than you wouldn't have variations that are quicker than something based upon how compact the image is. Because you have this inverse relationship between spatial domain and Fourier domain. And so if you see variations that are faster than what you would expect due to how compact the object is, then you can also attribute this to variations and try to study the variation in that way as well.
Monica, did you want
Can I ask you a question?
Yeah.
Hello. Well, we're getting into the nuts and bolts of this, but what I find really fascinating is the historical and philosophical approaches to this. I mean, I showed that your slide when I spoke today about what are an iconic images, but I've come to really appreciate that we do this EHT project within an historical context, and there are deep philosophical questions to ask, and where do you see that going in the future? I mean, you've played a more and more active role in the project.
Well, I think that one of the things that's really striking is that having an image has made such a difference. I mean, I think that you could say that, well, we've had a long historical move towards the reality of black holes. Each step has added to our conviction that these things are real, whether it's 1970 with Cygnus X1 or all of the things with the galactic center, including the orbits that UCLA and Munich have measured, and LIGO's extraordinary experiment. But there is something about an image that not only had this impact greater than we imagined on the public response, but I think also in the scientific community, there's something about being able to see, there's an open-endedness to seeing that addresses a need that we have to say not just do we suppose that something is true and then looking for confirming data or statistics or a chart, but actually to see something and say what might be there that we hadn't expected at all and what that might be. And I think these iconic images, the kind that you showed in this slide, whether it was Hooke in the 17th century or the early X-ray pictures in the 1890s, or even that you could say, well, everyone who draws a science fiction image could picture the Earth as it was seen from the moon, but somehow when we saw it, it affected us in a different way. These things opened up something about the world in a new domain. And I think that part of the power of the image of the black hole is that it wasn't just confirming data. It felt like we're seeing something, and that seeing allowed it to be other than what we expected. I mean, it's true, we can look at simulations and we can especially pick out ones that look like the image that we saw, but the fact that we saw something real, I remember I was talking to Monica at the image workshop in July of last year, and I think both of us were somewhat surprised by how moving it was to see the image, to see something real, even if you expected to see a shadow. And I think that's not just a public response, it's a scientific response too at the same time. This opening up of a domain that to what's unexpected. And I think that whatever is going to happen at this, our images of the center of the galaxy, that I think we're going to end up being surprised by things we see there amidst all these quickly changing phenomena. And I expect that to be less predictable than M87, but we'll soon know, I hope. I promised Avi that we would give everybody a break before dinner. It's a little after 5, and we're convening at 6, is that right? Since I have to learn to get up above 4. So see you in an hour for dinner. Thank you all for a great day.